These are the notes for 18.3, and we're going to be working with special types of right triangles. You know, our trig unit, we focused on right triangles and focused on sine, cosine, and tangent. With certain special right triangles, there are actually some tricks and some tips and kind of shortcuts we can use to get to our answers sooner. So the first one is an isosceles right triangle, and you'll notice in the diagram we have a 45-degree angle, a 45-degree angle. Those are the same, and since those are the same, the sides across from those are also the same. Okay, so that's where our isosceles triangle is. Now I know it doesn't look like the way we normally draw one, but it's okay, because again, an isosceles just means that we have two sides that are the same. And so an isosceles right triangle is sometimes called a 45-45-90 triangle. Because of the three angles that are inside of it. We have the two 45-degree angles and a 90-degree angle here in the corner. And the reason that's always going to happen is because, first of all, we're going to have a 90-degree angle because we're talking about right triangles. And in any, think of just a general isosceles triangle. If this is 90 degrees, right, this bottom one's x, that one's x. So 2x plus 90 has to equal 180. Subtract 90 from both sides. 2x has to equal 90. Divide by 2. So x has to be 45 degrees. Okay, so every single time you have an isosceles right triangle, they're going to be 45 and 45. Now in that 45-45-90 triangle, the hypotenuse is square root 2 times as long as each leg. Okay, so we have the hypotenuse here in green across from our 90-degree angle, and then each one of these other sides is known as a leg. So whatever the leg is, typically we'll use a as the variable here. Since that side is a, this bottom side must also be a, since they're the same. And your hypotenuse is going to be a times square root 2. Then the other special right triangle we have, before we move on from that, so to kind of wrap this up here in a small little box, our leg is going to be a, and our hypotenuse is going to be a times the square root of 2. Okay, so that's the big idea there, so you need to remember that relationship. And then if we cut an equilateral triangle in half, so if I take this diagram and we actually draw the other side of it, something about there. Okay, this will be 30 degrees, another 60 degrees. Okay, so this is our equilateral triangle, but if we take half of that, so if we're just focused on the left side here, there's a special relationship, and this is called a 30-60-90 triangle. Now, a 30-60-90 triangle is a little more complex, but we can kind of summarize it here in just a moment. First of all, the hypotenuse is going to be 2 times as long as the shorter leg, because you'll notice here on this one we have a short leg and a longer leg. So it's 2 times as long as the shorter leg, and the longer leg, in this case the one on the right hand side, is square root 3 times as long as the shorter leg. So essentially here's what we have. The short leg, again we'll start with calling it A. The longer leg is going to be A times the square root of 3, and the hypotenuse is just 2 times A. Okay, so those three relationships, again, to kind of just summarize that up here, the short is just A, long is a times square root 3, and your hypotenuse is 2a. Okay, 2 times a. And so you'll need those relationships. And again, if you can memorize those, you can always use your sine, cosine, and tangent, but if you recognize these special triangles and you remember these relationships here, you can actually do these much, much quicker than trying to find a calculator and use your trig ratios. So on the back, okay, again, the second page, a reminder for the 45, 45, 90 triangle. Your leg is A, and your hypotenuse is A times the square root of 2. And for your 30, 60, 90 triangle, your short leg is A, your long leg is A times the square root of 3, and your hypotenuse is 2 times A. Okay, so if we use those, that can kind of help us quickly identify these different side lengths. So example 1, find the unknown side lengths in each right triangle. As you see in the diagram, we have a 45, 45, 90 triangle. So from there, tells us our hypotenuse is 10. Well, if you remember up above, our hypotenuse was A times the square root of 2. So if our hypotenuse is A times the square root of 2, then we know that 10 has to equal A times the square root of 2. We're going to divide both sides by square root of 2 so we can get A by itself. Those will cancel on the right. On the left, we're going to have 10 over square root 2. And for us, for what we're doing, I'm all right with you just leaving it like that. Typically, as you go higher up in math, and we may talk about this eventually later on, but you won't want this denominator to be inside of a square root. And there's a way to do that, to work around that. I'm not focused on that right now. If you want to know, you can come and talk to me and I'll be glad to show you. It's really quick. But for now, that's good enough for me. And so in our diagram, 10 over square root 2, 10 over square root 2, and our hypotenuse was 10. Okay, just like that. Then number 2 is a 30, 60, 90 triangle. So first of all, you want to recognize that our hypotenuse is over here, our short leg is to the right, and our long leg is underneath. So our short leg, remember, is A. So since our short leg is A, we know that A is 5 square root 3. Now our long leg is A times the square root of 3. So if I substitute in this A, then we know our long leg is 5 square root 3 times the square root of 3. Now what happens here, when you have two square roots like this, you end up with square root of 3 squared. And the thing that's special about that is a square root and a square cancel each other out. And all you're left with is just 3. Okay, it's not 9, it's 3. So essentially when you have two square roots and you're multiplying like this, your square roots just cancel, and one of your 3's cancel, and you're just left with the first 3. Okay? So be careful there, that can be a tricky one to remember. And 5 times 3 is 15. So our long leg was 15, and we can put that in our box. Now the last one, our hypotenuse, is 2 times A. So our hypotenuse is 2 times A, which means our hypotenuse is 2 times 5 square root 3. And 2 times 5 is 10 square root 3. And that's that. Okay. I'll do one more with you here, and then I'll let you finish up the last couple examples on the next page. Number 3, again, we have a 30, 60, 90 triangle. This time you should recognize that what they give you is the hypotenuse. Our short side is down on the bottom. Our long side is on the left. And so our hypotenuse is 2a. So 4 square root 3 must be 2a. So if we divide by 2, 4 divided by 2 on the outside there is 2 square root 3 equals a. So our short leg a is 2 square root 3. Our hypotenuse, we already knew, was 4 square root 3. And now our long leg is a times the square root of 3. So that would be 2 square root of 3 times square root of 3. Again, our square roots cancel, as do one of our 3's. So we're left with 2 times 3, which is 6. And there we go. Okay, so it's nice because I don't have to use, if I remember these shortcuts, if I remember these relationships with a and a square root 3 and 2a and a times square root 2 for the 45, 45, 90, I don't need to use the trig to find those side lengths. Okay, you still can if you ultimately forget these, but they're kind of nice to know and they're really convenient as you move forward. So I'm going to let you try 4 and 5 on your own, and then if you have questions on them, you can ask about those in class. The second example, example 2, is on Pythagorean triples. A Pythagorean triple is any 3 numbers that satisfy the Pythagorean theorem. A squared plus b squared equals c squared. Okay, so to verify that these are actually Pythagorean triples, they give you 3 examples here. For example number 1, 3 squared plus 4 squared has to equal 5 squared. 3 squared is 9, 4 squared is 16, 5 squared is 25. So 25 equals 25. That is true, so that is a Pythagorean triple. And that's really the one you'll see most often. You might run into some other ones, but that's the one that's probably easiest to recognize. Number 2, again we have 5 squared plus 12 squared equals 13 squared. 5 squared is 25. 12 squared is 144. And 13 squared is 169. 25 plus 144 is 169, and those two are the same. Okay, so you can go ahead and try that with number 3 and verify that those are also Pythagorean triples. And if you can recognize multiples of these, then it's really easy to find missing side lengths. So for example, the one example down below, use Pythagorean triples to find the unknown side length. If you notice, both of these numbers here are divisible by 6. And so if you do that, if you divide both of them by the same thing, by 6, you get 3 and 4, which means that this would be a Pythagorean triple. 3 and 4 means that my hypotenuse has to be 5. But since they were all a multiple of 6, we're going to multiply this by 6, and that will give us 30. Okay, so that's kind of the nice thing. If you remember some of these Pythagorean triples, 3, 4, 5, 5, 12, 13. And again, we don't see them a ton, but if you can recognize them at times, they're just nice little shortcuts.